Hello and welcome back to another lecture. In this lecture we're going to go ahead design a form for a wall. It's could be abutment for a wall form, and the criteria we have: the wall is 14 feet tall, and the rate of placement we want to use is 3 feet per hour, and the time of the temperature for placing the concrete is about 60 degrees. We're going to design this based on ACI 347R-14. We're going to design this entire form from beginning to the end. First, we're going to calculate what is the pressure for a 14 feet wall. If you go into the table 4.2.2.1a parentheses A, in this table says wall less than 14 or equal to 14 feet should use this formula which I have here, CC times CW times 150. Go ahead and use this formula, and which is CC times CW, unit weight and a chemistry coefficient. They both come out equal 1 based on our design criteria from table 4.22.1a, and what do you have on here. And then we're going to plug in this number, see what we're going to get for CP max. So this is basically equal 1 times 1 times 150 plus 9,000 times 3 divided by 60, and that's equal 600 psi. Okay, now looking at the code A347R14, we got to find out this is more than minimum, and we got to look at the maximum and minimum limit. Looking at what I have on a board, this is satisfied the minimum and it's no greater than maximum, so this is what we're going to use for pressure. One thing you have to be careful, you as a designer, you got to be careful the spec. If this was 15 feet wall, the pressure would be a lot different than what we have here. So this is going to be, we're going to say this is 600 psi, and we're going to go ahead and get to work on design this form. The first thing we want to do, we want to find out the plywood sheeting. Want to know, this is my studs. I want to know what is the distance that I want between, maximum distance that I can have between my studs, and that way I can stay below that. And this is your plywood sheeting, and you want to use your plywood sheeting in a strong axis. So you want to basically, this is be a 4x8 this way. And your stud's probably going to go every either 12 inch or 16 inch, and we're going to look at it, see what is the distance based on the pressure we have, and we're going to calculate the bending stress on that. And then you have your whalers. That's another story for as we coming up. As you remember, we recall, we know the bending stress equal FB is equal MC over I, or is equal M divided by S. Bending moment normally for a single span was W L squared divided by 8. But in our case, we don't have it. We have it like a 3 span. So we're going to use the moment is equal for 3 span W L squared divided by 10. Design for bending stress, we usually go ahead and calculate the section module, and then we go ahead and size the beam. In here, we go a little bit backward. I want to know the maximum distance I can use, because I know what later I'm going to figure out what stud I'm going to use. And for the sheeting, I just want to know what distance for the sheeting I can use based on what I have. So we take this equation and kind of basically rearrange them. We know M is equal to W squared divided by 10 for 3 span. We know the bending stress is equal to M divided by S, and then we can calculate L for 3 span is equal to this equation right here, 3.16 square root of F prime B times S divided by W. The reason we have F prime D, because this is a timber, so we got to get the adjusted bending stress, which basically depend on based on NDS specification, the situation and the condition you have for the plywood. For let's say 3/4 inch plywood, and the section module KS from a table is 0.453 inch cube. And then we can go ahead and calculate this equation. We need to find out F prime B first. Of our weight, say we got the beam right here, and let's just put a load W, and that's been a tributary 1 foot section. On the plywood here, it's going to be on a 1 foot section. We're going to go ahead and say for a 1 foot section a tributary width, not this width here. It's going to be we have 600 psi, and if we multiply that by a 1 foot section, that makes it 600 pound per foot. And of course, we want to know what is that per inch. If divided by 12, it become 50 pound per inch. Now we can go ahead and calculate this, our FB prime. So FB prime from an NDS table is equal 1933 psi, as you can see from the table. And therefore, this equation comes out to be 3.16 square root of 1933 times KS came out to be 0.453. Divide that by W, which was 50. So that's going to come out to our L. It's 13.2 inches. We are using the allowable stress design, so the allowable span length, it's going to be minimum of a maximum of 13.2 inches. So we can use 12 inches. We're going to be well within that tolerance. Now we want to check the maximum deflection. See, the maximum deflection equation for 3-span is WL by power 4 divided by 145 adjusted modular elasticity times moment inertia. Now, we're going to say the limit for deflection either is going to be L over 360 or 1 over 16. Which one is the smaller one? We're going to take that. So we're going to set 1 over 16 or L over 360 equal to that. That way we can calculate L, and L become this, and find out what is the controlling length. So if I plug all this number, we have all these. We have E prime from the table. We have E prime is equal 1.5 million. Could be in DS table. E prime is equal 1.5 times 10 by power 6 psi. Moment inertia is equal 0.199 inch by power 4. So we're going to go ahead and calculate that 0.738. This is not a square root, but it's a 1 basically time, we can say this way, and that is 1.5 times 10 by power 6, and multiplied by EI. EI is, let me parentheses around this, 0.199, and then the whole thing divided by W, and W came out to be 50 pound per inch, and this whole by power 1/3. So the L comes out for this one 13.4, and L for this one is going to come out to 1.735. 1,500,000 times 0.199 divided by 50 and by power 1/4 comes out to 15.2 inches. So our deflection, this one controls, and from previous number came out 13.2, so 13.2 is a controlling one, which I erased anyway. Those of you who took steel design or timber design with me, when we design a beam, we normally check for bending, we check for shear, we check for deflection, we check for bearing. So we're going to go ahead and check for all these three. So we did check for deflection, we did check for bearing. Next we're going to check for shear. Let me erase this, and then we're going to go ahead and check for shear. Luckily we have table to go to calculate some of these design for. So for checking roll and shear from the APA table for class 1 plywood with load duration should about less than 7 days, we have the roll and shear of equals 72 psi, and from the other table we can find IB divided by Q is 7.187 inch square. 3 span, we have shear. We call that the, yes, remember we had shear in timber design, we had the, I'm going to put it on the board instead of drawing it. So it's the distance away from the end of the beam. So that shear, the equation is for it, 0.6 WLC. So now calculating the LC for the shear, it's going to be right here, and we said this came out to be 72 and psi times 7.187 and divided by 0.6 times 50, which is equal 17.25 inch. And we showed this right here before. We said that if this is the plywood, we have the studs going like here, and our stud usually is about 2x4 or 2x6. So it's a 2x4. That means if that's a 2x, then for 2x, the LB is equal 1.5 inches. And I have a piece right here. So you have your LB is going to be basically 1.5 inches, and therefore your total L is going to be LC plus LB, which is 17.25 plus 1.5, and that gives me 1875. So this is for shear, but we know the bending control. If we design it for shear, we're going to say, okay, the allowable length span is 18, but the bending says it was 13.2, so we're going to go ahead with that because that controls. We know the bending control and the length, the allowable length for the bending was 13.2 inches. Therefore, we're going to use for design, we're going to use 12-inch spacing between our studs, and that satisfies all the bending, shear, and deflection. You got to remember, and since we have a 1 foot spacing between the studs, and you have a 8 feet of plywood sheet, so the next piece of plywood sheet is going to come on this side. You're probably going to have a 2x4 stud back to back with each other. Next thing we're going to go ahead and look at the design is stud size. We said 2x4. We're going to make sure that size okay, and then the wailing spacing and size. We're going to work on that. We're going to go ahead and design this stud just like we do the beam design. We're going to go through deflection. First, we're going to go through bending, then deflection, then shear, and then bearing in this case. Also, all 4 criteria are going to be checked. And you're looking at this, the pressure coming outside of this stud, and the stud is backed by this whale, the whaler, and so this is a support system behind it. And then we can count that as a uniform distributed load, and our maximum is a 600 pound per square inch, or we can say it's same as a 50 pound per inch on a beam. And therefore, but the stud we're going to use is a 2x4 stud, standard size S4S. And if we go into table 4A in NDS, we find out the bending stress for this 900. But because it's a timber, we have to find the adjusted bending stress. And adjusting bending stress is basically f of b prime, remember from timber design, is f of b times all these adjustment factor. You can watch one of my videos and they talk about this in more detail. So we're going to go into NDS table and find out these factor. Because the condition is outside, the time is less than 2 months or whatever for the form, and therefore the adjustment factor comes out for CD is 1.25. The size factor, because it's a 2x4, comes out to 1.5, and CR become 1.5. If you just look on the table I have from NDS table, and the rest of the stuff probably is 1. So that's 900 times 1.25 times 1.5 and 115, and that comes out 1940 psi. So for table 1b from NDS, your section module comes out to 3.06, and moment inertia is 5.36. If we go from a previous step, so instead of calculating bending stress, we're not just going to ahead and calculate the allowable length stress, because we know the moment for 3 spans was W squared divided by 10. So anyway, the L comes out for, based on previous step that we talked about, 3.16 times square root of FB prime times S divided by W. Which is equal 3.16 square root of 1940 and 306 divided by 316, no, divided by 50. So our allowable bearing length is going to come out to 34.4 inch. So that's basically the support right here. If I give it a support here, and this L, it's going to basically come out to 34. So the distance between two whaler is going to be a 34 based on bending. But I don't know what about deflection, what about shear. So let's find out. I'm going to just go ahead and put the L down here. L for the whaler, for the stud. It's for bending is 34.4 inches. Let me erase this and we continue. So next thing we're going to do is check for shear, and FV prime is equal F of V, CD, CM. They all 1 except for the CD, so it's going to be basically F of V from the table. It's on a board. It comes out to 180. So that's 180 times 1.25 and equal 225. 225 psi. That's a 5. So now we know our shear is equal 1.5 or 3/2 FV prime times dB. And the shear itself, the point of thickness away from the end of the beam is 0.6 WL minus W times D plus LB divided by 2. And if we combine all those to calculate L, L comes out to this equation. And let's plug in and see what we're going to get. So that is 225. And time BD, and BD was 2/4, so it's a 1.5 times 3.5, and divided by 0.9 times 50 plus 1.67 times 3.5 and plus 0.83 time LB, and LB was LB is 2 of these, so it's going to be, you got 1 here, 1 there, so it's going to be 2 times 1.5. And therefore our L comes out to 34.6 inch. That's almost same as here, so this one controls so far. Okay. So far we did bending check, and we did shear check, and the bending so far controlled, and let's do a deflection check. Always you have to do deflection check. Do everything. So like previous step that we did, for deflection, we're going to set deflection in 2 different criteria. We're going to say either L over 360 or deflection of 1/16, whatever comes out the smallest. So the we set the deflection L over 360 equal to the equation deflection. That will give us allowable length is equal to this equation, which we did that in the previous step. So it's 0.378, basically by power of 1/3, or they show them like this way. E came out to 1.6 million, so 1,600,000. Run out of room here, and I came out for previous step. We had I as 536. I had it down here, 536, and divided by W, which was 50. So L for this comes out to 41 inch. So this still control. Let's find out what happened here. In here, it's going to be 1.735 by 1,600,000 times 536, the whole thing by power of 1/4, and divided by 50. So L comes out to 35.3 inch. So this one really controls. And that means the distance between the whales cannot be bigger than 34.4 inches. Before we continue to the next section, let's design this spacing. We said we can't be more than 34 inches. Let's say it's 30 inches. So we want to know what is the weight on the whales. Remember the turbo 3 area? We talked about that many times in class. Turbo 3 width, and we know the pressure is 600. But what is W? So W, it's going to be times the turbo 3 width. And the turbo 3 width of this is going to be 30 inches. So if I take 600 times 30 and make that to a foot, and that's going to come out to 1,500 pound per foot, or it's going to be same as divided by 12, it's going to come out to 125, or 125 pound per inch, which we could use better. So that's the pressure on the whales. And coming back, so we're going to go ahead and check bending. And the bending equation, of course, you know that is equal FB m over S, and from this equation, it comes out to, our suction modules comes out to WL squared divided by 10 times FB prime, and FB prime is, the what it was 900 PSI times adjustment factor becomes 1687. And therefore, we can go ahead and calculate the section module, which SS comes out to W is 125 multiplied by L squared, and L squared we said it's going to be the L, we're going to have 24 inches. 5 times the well span length is 24 inches 24 by power 2 and divide that by 10 times 1687, and that comes out to 4.26 inch by power 3. Now remember, this 4.26 is bigger than, remember we said S was 3.06? It's bigger than 3.06, but we're using a double here. So really, you're going to say 2 times, this is less than 2 times 3.06, so it's okay, it's not. So now we're going to check for share. I want to go back in here. I didn't explain how we got the length of the well is about 24 inch. You might think, oh, wait a minute, it's 1 foot. It's not 1 foot because the tie spacing, which is right here, and you have a tie right here, and you put a tie right here 24 inch apart, and this basically on the other side, they connect with, you have the same thing on the other side, and the tie is going between and locks up here, and therefore your support system is about, your span is going to be 24 inches, because remember, the stud is not supporting, the force is coming this way, coming outside. So basically, if you look at this, and this is your double whale right here, and you have your this is going to be your tie. It's like a support system, and then you have a stud, one stud right here, and then you have another stud right here, and then you have another stud right here. Okay, but the force is coming down this way, and your support is here, so this is a 24-inch spacing. That's why I said the whale spacing is 24 inch, and it's calculated right here. And therefore, after that, we're going to go check the shear. The equation of shear is the same as the one before, and comes out right here. And remember, when you do the D and LB, you got spacing between the whales. That's why those numbers are. You can figure that out anyway. So our L for that comes out to 28.5 inches. So now we're going to go ahead and erase this, and we're going to go ahead and do a tie design. You say, how did you come up with the, we said 24 inch apart, and let's see, the spacing between the ties is 24 inch. Just double check that out. So the reaction here, based on beam formula, is 1.1 WL, and the tie spacing equation is tie capacity divided by whale load, and we said the tie was 3,350 pound self-working load tie, and divide that by the reaction, comes out to 24.3 inches, so we're good right there. So now we checked everything. We checked all the stuff. Another thing we're going to check, we talked about a couple of weeks ago, is the bearing. Because you got this tie and it's pushing on a whaler and then pushing on a stud, is it going to break that stuff? It's going to crush it, or is it going to make it? So let's do, I'm going to erase this, and we're going to do a bearing check. Now we're going to go ahead and check the bearing stress. And if you look at a 2x6 plate, you have the studs, and then we're going to, the maximum reaction that is going to be on the tie that has, which is right here, push pressure on this plate is 3,300 pound, which we calculated from previous step. And 2x6 inch plates we're going to use, and then from NDS, the bearing stress or compression stress perpendicular to the grain is time the adjustment factor comes out to 743 psi, and we know stress is equal force divided by area. So I got 3,300 divided by the area. Area was 6 inch, which was just calculated right there, which is 2 by 3. Because it's inch and a half, you add them up, become 3. So the area is 6 inches, and that comes out to 550, and that's the bearing stress, which is less than 743. So we check that, and we're good over there. So this is the pressure of the bearing plate on top of the whalers. Now the whaler itself, right, this whaler, 2 of them, pushing on a stud. So let's figure that out. See how much that gonna comes out to. And we want to know what's a stud on the whales, and the bearing area on top of the stud is these two whales are going and pushing on a stud underneath. So the area, what's the area of these two right there? And that's two of them, and multiply by 1.5 times 1.5, because this is 1.5, and a stud underneath is also 1.5, not 2 inches. The stud is 1.5. So it's 2 times 1.5 times 1.5, and that is 4.5 inch square. So now the RB, the force that it's on a stud, so the force on a stud is a WL, which is base, so 50 times 30, and that's 1,500 pound. Then we're going to have the compression is going to come out to 1,500 pound. Divide that by the area, which came out to 4.5, and now we're going to have 333 psi. And our LB come out to be 2 times 1.5 plus half, was equal 3.5 inches, the bearing length, because we have two of them, and then you have the gap between it, so that becomes 3.5 inches, and therefore our compression comes out to the bearing compression comes out to 625 times what was that adjustment factor we just said? 190, 1.1, 1.1, which comes out to 644. And that is more than 333, and we check out. So going over this step again, we did the bearing check on the plate on whales. Then the whale itself put pressure on the stud. The area of the stud was basically these two square right here, which we figured out, which was 4.5 inches. And then the reaction is based on the 30-inch span. And that came out to 1,500 pound, and therefore the stress comes out to 333 psi. It has to be less than the compression stress of the bearing stress of the material, which is anyway, I wouldn't even multiply by this because it's less than that, so you're good. This was a long problem, so when you do this as a designer, be very careful. When you design something, be conservative, because if the construction guys, they do a little bit different and if something go wrong, they're going to complain it was the designer. And make sure you follow the code step by step. And if you have a question, don't be afraid to be conservative. Hope this was useful, and if it was, please give me a thumbs up.